I'd like to introduce our first speaker, Nicole Jackson, who will present on weather impacts on utility scale photovoltaic plant performance. Nicole, go ahead and bring up your presentation and we will get started.
All right. Okay. I can't see anything, so I'm assuming if everything is good to go.
It's good to go. It looks good. Thank you, Nicole.
All right. Thanks for the introduction, John. And it's great to be here with everyone. It's morning where I am, but hope everyone's having a great day wherever you are. And so as John mentioned, I'll be speaking to you on weather impacts on utility scale photovoltaic plant performance. And I am currently a member of the technical staff at Sandia National Laboratories. And so before I dive into the technical material, there's lots of people I'd like to thank. First of all, my co-author on the work, Tushar Gunda, who's also a staff researcher at Sandia, and Andrea Stade, who some of the future work I've been working with on her end, as well as Joshua Stein, who's provided invaluable PV-related technical insights. And we also have some external collaborators at NREL and Lawrence Berkeley and our sponsor DOE. And this project does rely on lots of public data on the weather side, but there's a lot of industry data that I'll also go into some detail on. And so without all of the folks and their companies on the right-hand side, this project definitely wouldn't be possible. So lots of thanks and gratitude to be able to share this work with everyone. And so, as the title alludes, I'll be talking about weather events related to solar power plants. But let's take a step back and think about what sorts of disruptions in general can happen to power plants. And so on the left side, you'll see damage at a PV plant that's located in St. Croix during Hurricane Maria a couple years ago. And you'll notice that the panels have separated from the framing, and in general, the panels aren't going to produce any more energy. And so what ends up happening is there's a series of financial implications that arise from these types of events. And so when we're thinking about it from the insurance side, which is where some of these damages kind of propagate in terms of record-keeping, weather-related events are almost half of all insurance claims within the solar industry. So these events are important when you're considering the impact on potential energy generation, as well as the financial side. So when weather events happen, it's costly. And so with that in mind, it actually led us to having an overall objective of how can we kind of ingest maintenance records from these different sites, along with their production data, along with weather information, and perform an integrated assessment to understand how does solar power plant performance change as a function of weather events over time. And so with that, there's a lot of data that I mentioned earlier. And so we start with the operations and maintenance records, and I kind of liken it for folks who aren't in the maintenance side of things. It's kind of like having a diary entry of what happened when and what might be some of the causes of different issues. And so you end up with a time series of text records that describe these events. And so from that, we were able to identify general patterns and key events of interest. And we also couple that with our industry partners, the production data, which is also time series information. And also feeding into different types of weather data from point location to gridded location, as long as some of the sites do also keep track of their own temperature and wind speed and so forth. And so we combine all of that into a massive panel and then do some bread and butter statistics along with some machine learning. And the machine learning was a two-stage approach, as I liken it to. So the first part was creating random forests, which allowed us to identify key features. And then the second part was using a local interpretable model agnostic approach, which helps us provide improved feature descriptions for the selected features that we've identified as being important. And so I'll walk you through a couple of different results from that as well. All right, and so on the utility scale side, for what kind of data do we have that describes the power plants themselves. And so there's two sets of data that's provided by industry, the operations data and the production data. And so the two maps at the top show the spatial distribution of where this actually occurs throughout the continental US. And so we consider the data set that we have here at Sandia to be fairly representative, and that we've got lots of sites throughout most of the country to be able to generate some overall trends for the entire US. And so on the bottom of the table, it's just some quick highlights in more detail of the data set itself. And so one thing I do want to call your attention to is the time period in which we're dealing with. And so there's a mismatch in records between the maintenance side and the production side. But generally speaking, our times period covers August 2014 to February 2020. And then we have towards the latter half of that, we have corresponding production data. And altogether, we've got 54,000 text entries on the operations side. And then on the production side, we have also 54,000, but these are actual daily records that we've accumulated. And the production data actually comes in at a couple different finer spatial temporal resolutions, but we have 54,000 production days. And so the first part is, how do we know which events are important? Because when you're dealing in the weather space, it's almost like you have too much data and too many events to consider. And so we use the O&M records to actually, through natural language processing, help us elucidate which of the events are most important. And what you'll see here is a chart that shows the prevalence of these key terms within the records themselves. And through that, we narrowed down our analysis to cover hurricane, snow, and storm. And storm is I think this group of folks will find it to be a somewhat funny term, in that in industry, it's kind of used in a very colloquial way to cover anything when almost a day isn't sunny. But for those of us that enjoy weather, we tend to take a more nuanced approach. So the storms is kind of our catch-all, if you will, just to match what is happening on the ground. And so we've got lots of data that we're ingesting, and this massive table gives you a flavor for all the different types of variables that we considered. And so one thing that I'll call your attention to is what we call our climate variables column. So it's the second column, or third column, sorry, on the chart, third from the left, and that we use publicly available weather data to kind of construct lots of different variables. And so we've got daily snowfall, which is essentially the total snow that fell, but then we also converted that data into a net daily snowfall. So taking into account that most of the PV production happens during the day, which also coincides with when you'll have, for example, snow melt. And so that net snowfall daily takes that into account. And then we also did a running tab of how much snow has fallen at the site over its lifetime. And some of our records showed that when you have snow and it hangs out, it essentially creates this load on the panels, which over time can cause issues. And then similarly for hurricanes, we also came up with a couple of additional weather variables, namely the number of days since the last hurricane. So as you saw from some of the maps, our particular data set has a lot of sites that are located in the Carolinas on the eastern seaboard. And so they're prone to experiencing these events. And so we wanted a variable that captured how many days since that particular phenomenon occurred, and also how many days since you had any sort of rain as well. And similarly with storms and floods, we ended up grouping the two together. There was a lot of coincidence within the operations and maintenance tickets themselves. And so we ended up just kind of collapsing it. And so you'll also see some additional how many days since this particular type of event occurred, and some binary indicators. So depending on the data set we were using, even though we had sub-daily data on the production side, and it's possible to resolve down to the minute the operations data, we ended up just doing things at a daily scale and kind of overlapping. And then also, I'll call your attention to some of the what we call metadata variables, which are these kind of plant level descriptors, if you will. And so for each site, we took into account NOAA's climate region, and there's a researcher, I'm drawing a blank right now on where he currently is located, but essentially thinking about where the site is located, there's solar specific climate zones that have been developed. So that's what the PV climate zone is. And it's a function of, here's where you have different bands of wind, different bands of humidity, and different bands of temperature. And so it's actually like a 3-class grouped classifier. And each of our sites was also lumped into one of those, as well as the usual Köppen-Geiger climate zones. So lots of different things going on the weather side for this work. And so if we take a step back, and our goal is to just look at how the performance changes. And so what we did is we calculate what's called the performance ratio. And it's basically a comparison of how much energy did you generate for that given time period divided by what the facility should produce based on, here's what's installed. So they call it, in PV speak, it's called the nameplate capacity. And so it's just a quick ratio that we do. And so you add up all of the production for the day and divide it by what that nameplate capacity is, and that will give you the performance ratio. So in this case, the closer you are to 1, the better. It means that you're operating at pretty much your full capacity, and then the lower it is, the poorer the performance. And so what you'll see is that we do have different responses and different responses as a function of each of the types of events. And in this particular case, based on the data we had access to, storms generally have almost a 55% reduction, or I'm sorry, snow has almost a 55% reduction compared to a non-snow day. Hurricanes, it's about a 13% reduction. And then storms, we actually saw in our data will result in almost a 1% increase. And that's kind of counterintuitive in that you would think that due to the clouds and different weather conditions that you would see a reduction, but it turns out that due to operations and maintenance activities, these panels aren't cleaned very often. And so the presence of a storm actually helps remove dust and other debris that's kind of coated on the surface that's collected. And so storms in this particular case result in a minor increase in production. So that was a cool finding. And so all of this comes from just traditional statistics. But quickly, I'll go through some of our random forest results. And so what we did is kind of started out with the big panel from the table that I showed earlier, and essentially for each of the events toggled on and off different variables to boost our accuracy. So our goal, to be clear, was not to come up with a performance prediction model in this case. We were just looking at different nonlinear combinations of events. And so storms actually ended up with the highest amount of accuracy, but that's because we had far more variables than we were including, and we think that it's just a more robust model that was generated. But some things that I'll call out is that you see differences in the types of variables that were deemed important and how important they were.
Nicole, sorry to interrupt. If you could wrap up in the next minute or so, I'd appreciate that.
Thanks, John. And so actually, I only have 2 more slides. And so we use Lime, and that helps identify within those features that are important, the ranges that are important within themselves. So as I mentioned earlier, we have a bunch of variables that kind of fall under the nearest, so from a particular event. And so Lime was actually used in the case you can see in hurricanes, 3 days since, or our plant was 19 months or so forth. And so that was our approach on doing this integrated assessment. And so we actually have a paper that's come out, and I'll post a link to it. It's open access. I'll post a link to it in the Slack group. But this work is continuing, and some of the events that we're now focused on are wildfires. But the important thing is we have successfully integrated operations records, production records, and lots of different weather variables to understand how we can have low performance on different weather event days. So thanks, and I'll take any questions.
Thank you so much, Nicole. What an interesting topic, and so timely as we really need to ramp up our renewable energy production in order to have a chance of addressing climate change. Yes. I welcome everyone just to take a few seconds here to sort of reflect on what you've heard. And one trick that I sort of use for myself, because I'm a bashful question asker, is if I were going to ask a question, what question would I ask? So you're not on the spot, but what what question would you ask if you were to ask a question, and then go ahead and drop that in our Slack channel. I don't think we'll take time to go through those orally right now. We may have a few moments at the very end of the session to take additional questions, but let's turn the discussion to the Slack channel for now. And I will introduce our next speakers, who are Amy McGovern and Jason Hickey, who are going to speak on lessons learned while creating cross-sector partnerships for AI for weather. Welcome, Amy and Jason.
Hello, Jason, are you also on camera?
Yes, I'm here.
Okay, there you are. The Zoom doesn't show you, unless you start talking. Okay, so we're going to introduce ourselves, and we have a third ghost speaker who's out on paternity leave. And so we had this idea for this talk, and we conceived of it because we were talking about all the ways in which partnerships across the different sectors can go right and can go wrong. So I'm Amy McGovern. I'm at the University of Oklahoma, and recently also doing visiting faculty position at Google Research, which is one way in which I learned a very big difference between the sectors. Jason's turn.
And I'm Jason Hickey. I lead the AI for Weather and Climate team in Google Research, and we're working with Amy in a couple projects that we'll discuss today. Sid Bukabara is a senior research scientist at NOAA, data assimilation scientist at NOAA Nestis. He's on paternity leave, so Amy and I are going to cover for him in this talk.
Now, if my slides advance, okay. So what we wanted to talk about for the different sectors, we'll start with, why did the sectors want to even work together? What are their traditional roles? Traditionally, academia has the long-term focus, and I'm speaking for academia. Jason's going to talk for private industry, and we're sort of going to take turns speaking for Sid since he's not here. Academia traditionally has the 5-year grants, the 3-year grants, the longer-term view. We'd all like to get 10-year grants. That would be great. But our job is also to not only look at this long-term view, but to train the students and the researchers that get hired by the other sectors. For private industry, they have a much wider reach. They can typically, we'll talk a bit about research operations. They can do, if you think about Google and how many people Google reaches, it's much different than just a single university. But their focus is often different and their timelines are very different. And we're going to talk about that when we're talking about how to make the partnerships work. And then for government, typically, now we're doing this as a typical answer, right? There's different answers to different parts of the government, and we can have that discussion. But typically, government is often interested in the infrastructure investment. So they're the ones who are putting up the money to put up the satellites. Again, there's some private industry who are doing that, but typically this is government. And when we're looking at NOAA, although there is definitely a research focus, there's also an operation focus, which is different than the other sectors. And there we go. By putting all these sectors together, we can leverage our different types of expertise. So looking specifically at AI and weather, we have a lot of expertise in AI and the physical sciences, but we have different focuses on our different sectors. And by putting ourselves together, we have creativity, because by having all these different expertises, we get more creative answers to the problems we're trying to solve. And these different perspectives inform each other. Academia sometimes thinks that they know what's most important. It's the most important academic problem. But when they actually talk private industry or government or operations, they find out that, in fact, that isn't what's really important, and that there's something more important that can inspire the academic research cycle. And finally, when we're talking about value, knowledge transfer is really important, because academia is not super well known for research operations. And both industry and government offer research operations opportunities. And then while we're thinking about academia sometimes being in their silo and thinking things, if they're actually working with private industry and government, they can actually know what the needs are for the people they're trying to hire, and thus influence the training and the academic degrees and classes that are being offered. So before we jump into sort of some of the lessons learned on both the good and the bad side, we were going to mention 2 successful partnerships that both Jason and I are involved in, so that not all has been roses. We have had our hard parts, which is part of what's driven this presentation, but 2 partnerships so that you know where we're coming from. So the first one is our NSF AI Institute. I'm the director of this institute, and you can see from this slide, probably a bunch of you have heard me talk about the institute, so I'm not giving an overview of the institute. What I wanted to talk about is, because what you can see from this slide is that we have partnerships across a wide variety of sectors. So we now have 8 academic partners. We have our federally funded research lab. We have government partners because we're working with NOAA. We're funded by NSF, which means we have NSF needs we need to meet. And then we have a variety of private industry partners that are listed on this slide as well. And we will talk about much of what we had to do to turn this into a successful partnership in the later slides. And I will let Jason is going to talk about the next one if my slides would advance. There we go.
Good. Yeah, and actually I want to give kudos to Amy for being the lead PI for AI to ES. As you can see, this is a huge organization, and Amy has been a great leader in bringing coherence to that. Another project that's very exciting and very successful is a collaboration between Google Research and NOAA Nestis on using AI methods, AI techniques to enhance weather forecasting, global weather forecasting. We're focused really on several really interesting areas using artificial intelligence techniques to increase the effectiveness of data assimilation. Roughly only 3% of our observations from satellite observations are utilized currently. We'd like to use AI to improve that amount of data that we can make effective use of. This is an OTA, Other Transaction Authority. It's congressionally approved project collaboration supported to focus on this research area. And next slide. And
why? There we go.
So what, at the high level, that there are explicit reasons why we want to work together. So Google brings, for example, expertise in artificial intelligence methods and technology, very large scale computation platforms, data processing, cloud platforms. And also, as Amy mentioned, we have an incredible reach out to the public and an opportunity to transfer these research objectives to the public. So the collaboration explicitly brings in expertise from other areas, domain expertise that complements our technology and leads to the development of innovative ideas and products. This talk in particular, we're going to focus on the challenges that come up. And these tend to revolve around things that are implicit. So our explicit reasons for collaborations are there. We work with them on a daily basis and we understand them, but they're implicit things that inform how we interact and that differ across sectors. One is openness of research. Private sector is much more closed around around research than public and the academic sector. Timescales are very different. Incentives for research are also very different. And we're going to cover many of these. Now, during this time of COVID, these implicit differences between organizations would normally come up in an informal way through meetings and discussions and maybe in the hallway. And if there are problems, then you discuss them on a as needed basis. During COVID, this is much more formalized, that you have to create a meeting and you have to put this on the agenda. We want to talk about this project. And so it was much more important for us to be very clear about issues as they arose and to address them squarely. Next slide. Okay, one is around intellectual property. And I have to say, so, on the industry side, the normal mode of operation is private, is closed, is proprietary. So we develop products, and if you come to Google and you collaborate at Google, you will see presentations around product development that are not publicly known, and this is the default stance. And the agreements that we form are usually proprietary and covered by a non-disclosure agreement. Now, the projects that we talked about in this that we're discussing here are open projects. They're open source. It's CC0. CC0, Creative Commons 0, is effectively public domain. So this is a non-standard kind of agreement. And this turned out to be an issue at Google to develop an agreement where all the scientists are on board with being open, but the corporation itself has some reluctance to do that. So in some cases, these negotiations to create open agreements took a long time. They're possible, indeed possible. And I think if this is very clear going into it, it's possible to set the terms for an agreement up front to accelerate the development of a IP agreement, but it needs to be addressed explicitly because the default path is closed and proprietary, at least for industry.
Yeah, and I would add to that that the default path in academia, at least in the sciences, tends to be open, right? And so we give the example of the negotiation can take years. It really can. The lawyers can get really involved in the nuances of this when the scientists just say, we just want to work together. And it can be very frustrating. The AI2ES Google agreement took a while. I can't remember how many months it was. And then your Google Leap agreement took a year plus.
Over a year, right.
Yeah. So when we say they can take years, we mean it.
Right. And as scientists, of course, we're eager to get started and work on things that really we're excited about. Okay. What's our next slide?
I think that we were sharing this slide. So one of the other differences, so after the IP differences, we've been talking, these all come down to the slide a couple of slides ago, which is that the culture is just very different across the sectors and you have to acknowledge it. And we mentioned this one earlier, when we're talking about timescales, and I'm going to use AI2ES as an example, academia looks at multi-year grants. So we're thinking multiple years out, not just about the next quarter or the next year, but we also have to apply for these grants, and getting funding is at least a 12-month process. You have to think of the idea, you have to write the idea down, you have to apply for the idea. Usually there's only one call a year. You have to wait for it to get reviewed, and you have to hope you get funded on the first round. You know, it could be a several-year process before you can do this thing together that you thought about. Well, as I'm learning in working with Google, you know, Google might have moved on a year from now. Now, fortunately, they haven't. They're still working on AI for weather for what we're doing. But, you know, if you conceived of one particular project, maybe they've made huge leaps and they've just moved on to something completely different. And academia is still sitting there saying, hey, we wanted to work together. And at the government level, it's very different because their request, that we're trying to speak for Sid on this. If you're trying to ask for new money for the NOAA level, it's a multi-year process because you have to ask for money at the federal level. So you have to approach this for multiple years in advance.
And, you know, on the private sector side, I'll agree to this. So, you know, the prospect of entering into an agreement that might take 2 years, we have no idea where we're going to be in 2 years. It might be entirely different from the place that we are now. We're very reluctant to make an agreement that pins us down 2 years. One of the wonders of the private sector, I was faculty before I came to Google. One of the wonders is this agility, the ability to move very aggressively into new areas as opportunities arise. And this is really wonderful, but it also is in tension with the long-term commitments. And in some ways, like with the AI2ES agreement and Google research participation in the NOAA OTA, we don't take money because we're reluctant to make contractual agreements, long-term contractual agreements, which affects our role in these organizations.
And I see that John has showed up, which means we are talking too long on each slide. So we're gonna get through. We have 4 more slides, John, but we're gonna do it because you know me, I can talk fast. So the next thing we wanted to talk about, and we'll do it faster, is that the different sectors have different incentive structures. Academia is typically rewarded for publications and research dollars. We're rarely rewarded for R2O. You might get a little bit of a pat on the back if you make a patent, but you know that's kind of it. Government has completely different rewards. So if you're looking at the NOAA mission, you know, you want to improve your forecast skills, you get rewarded for that. You get rewarded for your data utilization. You get rewarded for your R2O. I'll let Jason speak briefly to the reward for private sector.
And in the private sector, it's quite amazing. So one of the most surprising things perhaps is that we have twice annually, we have performance reviews that evaluate your performance for that cycle. And these are based on impact and leadership and the complexity of projects that you're involved. And so there's a constant drumbeat of evaluations that come, and we want our research collaborations to provide opportunities for career growth. This is very rapid. Okay.
Sorry that I don't know what, my mouse decided to scroll through a whole bunch of them all at once, which was totally accidental. There we go. We're going to go back. That was completely accidental, but I know that we're quick. So this was Jason's slide.
We'll be quick about this. Coding in industry, especially at Google, is very rigorous. We have high degrees of testing and coding standards. These do differ in research. There's research and operations. Operations has very tight coding standards. Research is a little bit more relaxed, but still these are typically differ from our partners.
And I was going to give a short story with just that, just writing hello world at Google is not one line of code. And that's all I'll say because we're out of time.
That's a week of code. Yeah.
It's a week of coding. Once you learn how to do it, it's not that hard, but boy,
Right.
is it a lot different. So the other thing, the quick thing at the very, actually, we'll just go to the last slide because I know that John's going to show up. So our lessons learned is that we need to figure out what we want to do early. And that was the slide that we were just about to talk about. There's a whole bunch of different funding mechanisms and you need to identify that really early. You need to identify how well you want to work together. You need to coordinate early and often, and you need to push your lawyers to encourage innovation because the lawyers really, in my opinion, don't want to do that. And my final point, because I know John is standing there, is that we need to find a way that facilitates long-term collaboration outside of the box that we typically think in. We need to, as a group, try to facilitate something new that can really make innovation happen more quickly. And that's it. Thank you.
Thank you very much, Amy and Jason. What good points. And if we can figure out how to work together better, there's so many ways that we can add value to the climate enterprise. So thank you very much. Let's move in the interest of time directly on to our next speaker, Julien Brajard, who will speak about combining machine learning with data assimilation to improve numerical models and estimate the system's state. Take it away, Julien. We see your first slide, but we don't yet hear you. You may need to unmute.
If I unmute, it
there
can
you
be
go.
better.
Perfect. Perfect.
Thanks. Okay. Yes. So I was saying good morning, everyone. And yeah, I'm Julien Brajard, and I will present you a slightly more technical work on, and more maybe a bit more theoretical too, but with a practical aspect, I hope, about combining machine learning with data assimilation. So the idea is to combine machine learning and data assimilation to improve the numerical models. So for example, numerical weather forecast, and also estimate the system state. So both are improving the model and the estimate of the state. So this is motivated by, okay, sorry, okay. So this is motivating by it starts actually from data assimilation and machine learning, and we observe that improving the state of the system and improving the dynamics or the estimation of the dynamics of the same system has been addressed with seemingly different tools, and depending on how much data you have and how much trust you have in your model, let's say your numerical model. So basically, if you have like a close to perfect model, a very accurate model, and few data of the systems, that you can use data assimilation to estimate the state of the system. On the other side of this scheme, if you have a lot of data but you have barely no idea of the dynamical model behind those data, you use classically machine learning to infer a numerical model. If you have something in the middle, so you have quite a lot of data, but they are still noisy and sparse, and you have a model that you trust not too much, there you're in the realm of the mixing of data assimilation to estimate the states and machine learning to estimate the model. So a lot of work has been done on that, and I will try to show you what we are doing here. So I haven't said it, but I'm working at NOAA Center, NERSC in Bergen, Norway. So I'm in Norway right now. And I will try to just show you what is our point of view. There will be few equations, and I hope you like it as much as I do. So let's say here that we have a numerical model. So basically, it's generally presented in the form of computer code that predicts the future state of the system. So temperature, pressure, for example, knowing the past. So you have a physical model that from the X, the state at the current time, predicts the future state. Of course, this model can have error. And if you want to improve your forecast, so the forecast here is the XK plus 1, so the prediction of your system, what you can do is improving, of course, the model itself by improving the physics of the model, improving also the initial condition from which you start of your model. Or you can also try to estimate the error. And that can be done if you have, for example, something somewhere high resolution models that have run for a very precise period of time, or if you improve the parameterization of which is not resolved by the physical model. So in all those fields for improving model physics, estimating accurate condition, and estimating the error, and especially the two last one, you can use data to estimate the initial condition and to have better initial condition. And this is what is done traditionally in weather forecast, numerical weather forecast community. But you can also use data to emulate the error of your model, either completely emulate your model or partially if you have already a model that is known. So this is what we are trying to do, and we will so focus on the error, the emulation of the error of your model. So how can we do that? That's pretty simple idea. We will try to represent the model error using a statistical process that could be a neural network, for example, that depends on parameters A here, that will try to reproduce as best as it can the model error. So you will have at the end a hybrid model, which is the sum of the physical model, so the process that you already know, and the data-driven model that has been learned from data. So I just want to specify two particular cases. If you don't have any physical model, so it's pure emulation problem. So you just learn from scratch a new model to estimate the next step. So this is the emulation, what I call emulation in the following. And if you have a numerical model, so this is the parameterization case. So you try to parameterize the error model. And because we like difficulty, what we had here as a problem is, of course, the data you have to estimate this problem are not perfectly known. So it means that you don't have data everywhere and you don't have perfect data. Data have noise. So still equation, sorry for that. So what can we do? We have some observation Y that are related to the state of the system via an observation operator H. That can be the most simple case is it's a subsampling operator. So you just observe few points on your state. It can be more complicated than that, of course. And you have on top of that, you have an error. And what you are trying to do is to estimate both X, which is unknown because you only have the observation, and your hybrid model, which is unknown because you have a data-driven part. So if you put that in terms of minimization, because we like minimizing stuff both in DL community and in machine learning community, you have two terms. One is you minimize the observation error. So the state that you are estimate should reproduce as best as it can the observations. And you try to reproduce your dynamical model. So the state you are predicting should be the closest possible to the state that you observed. And you should estimate both X, which is the state of the system, and A, which is the parameter of your data-driven model. I don't detail, but there is a full Bayesian framework to arrive to this to have this type of equation and minimization. So now we have a cost, so we can find an equivalent cost function. So we try to minimize the data-driven model should minimize the error of the model, and we also minimize the observation. Here, of course, we have the case where the physical model is perfect, so we don't have a data-driven model. So basically, if you do that, if MDD is 0 here, you just minimize the error and the observation, and this is exactly what we do in data assimilation. So this is what has been done for dozens of years in data assimilation. So this is the traditional data assimilation approach. And if you have perfect observation, so you observe the full system with no noise, or even with a bit of noise, that works too. You just minimize the error. You just have to estimate the parameters. And this is a very classical, very simple supervised learning problem in machine learning that you can do, for example, with this is a mean square error. So you just put a neural net and you do the traditional minimization. But what we're interested in the problem when neither the physical model is 0 or the observation are perfect, of course. So what we do is we solve the problem, but what we have called coordinate descent. So there are several papers that give more details about this process. So basically, we will do both things. So the DA step to estimate the state of the system, and the machine learning step to estimate our model, the parameters of our model. And we iterate between all those steps. Each time we choose an initialization for the parameter of the system. We estimate the state using data assimilation. I don't know if you see my cursor. I will assume you do. The machine learning step will learn the model. So you have a better A, so you can have a better DA, better ML, and at the end you converge with hopefully the best estimate, both for the parameter of the system and for the state. Of course, in the case where you have already quite a good model, the first DA step will be quite good. So you don't need to cycle. You can do only one. You don't have to cycle back on the DA step if your physical model is done. And this is what we have done for the parameterization case. So hopefully I have not been too long, neither too short, and I will show you some application of that. So the first application is the full emulation. So we don't have any physical model here. So we try to reproduce, it's a pretty simple Lorentz 96 model. So this is the evolution of the model of the true evolution of the model. So from this model, we have generate some noisy and incomplete observation, as you see here. So you see here the noise of the observation. So the challenge here basically is to reproduce this from this noisy part. And it's not only a problem of interpolation, because when you do that, you also want to have the model that is able to predict the future, so to make some skillful forecast. And so I have mentioned that we cycle over DA machine learning step, and this is what I will try to show you now. If you start with one cycle of DA machine learning, you have a pretty bad performance in forecasting. The Lyapunov exponent gives the representation of how you reproduce the dynamics of your system, and it's pretty bad too, because it's far. The range here is quite far from the true value. And if you see the surrogate model, it looks very different from the two model. But if you iterate like 50 times in that case between DA machine learning, you improve quite well your machine learning model. So you gain some forecast skill. And you also reproduce quite well the underlying dynamics of your system. So you have learned both to reproduce some state, and you have also learned to make some skillful forecast, and you have a good representation of the underlying dynamics. So this is the case of full emulation. We don't have a physical model. In the case where we have, so this is what this is a summary of what we obtained. So we are able to predict. So this is now the case with when we have a physical model and we want to emulate only the unresolved part. So we also apply the two-scale Lorentz model. So basically one scale is something that we assume to be known, and the second scale should be emulated. And here you see on this curve here, for example, the sensitivity of the method. So if we have perfect observation, we are able to have a quite good skill. So the error with respect to the lead time is quite low. If we only use the physical model, this is the red curve, so it's quite bad. And here in the middle, you see that even with a sparse and noisy observation, we still gain some skill with respect with the physical models. I'm out of time now.
Please wrap up in the next minute or so. You can take a little bit longer.
Okay, yeah, I should do that. We also did the same experiment with a more complex model, which is a coupling between ocean and atmosphere model. And you see that for the ocean, so for the slow process, we improve a lot the forecast skill with the hybrid model with respect with the trinkotic model, which is only the physical model. And to finish, we also did that with the QG model. So we add noise to the model, and you see that after 1 hour of integration, one day or 2 days, you have some error in the model. So it's quite nice to see that the errors are not completely random. They have some patterns, and those patterns can be predictable. And this is what we have predicted using a neural net and a hybrid model. So this is on the top row, the real model error, and this is a prediction of the model error. So it seems very good in terms of patterns. There is still a bias in terms of intensity, so we don't reproduce the whole error. Okay, so now I'm going to my conclusion, but if you need more details, there are publications for all those aspects. So the idea is when with noisy and sparse observation, we can combine data assimilation and machine learning to both reproduce the state of the system and to improve the model itself, which was not done standardly by data assimilation. And yeah, and this can be done even if you have already a physical model that works. There's a lot of other aspects that I have no time to address here, but that are still worth having a look, which is online learning and reproducing the climate. And there are some remaining challenges, and I'm done here. Thanks for
Julien, thanks so much for that interesting talk and for helping us see that synergy between data assimilation and machine learning and how the machine learning concepts can really help with the modeling. That's just really very interesting. In the interest of time, I think we're going to move on to the next speaker, but please pepper Julien with questions and comments in the Slack channel. Our next, okay, go ahead.
Sharing. Yeah.
Thank you, Julien. Our next speaker is Rose Yu. Rose, I invite you to go ahead and share your presentation. And Rose will be speaking about physics-informed deep learning for turbulent flow prediction. Take it away, Rose.
Thank you, John. So hi, everybody. My name is Rose Yu, and I'm an assistant professor at UC San Diego Computer Science Department. And I direct the Spatial Temporal Machine Learning Lab. So there's a lot of excitement around deep learning, and I do teach deep learning in my class. But in today's talk, I want to argue that when we model climate phenomenon or weather patterns, it's not enough just to use deep learning, but we also have to consider the underlying physics of the phenomenon, and that leads to today's topic, which is physics-guided deep learning. In the past few years, our group has been working on the learning framework called physics-guided learning. The idea is that physics as a discipline has been used for many decades in modeling climate behavior. So we often rely on first principle models to design model-based approaches for describe complex dynamics. So there are a lot of tools such as tensor networks, differential equations, and symmetry that are used in physics, but physics models sometimes can be computationally expensive. And they also rely on rigid assumptions, which might be very far away from real-world data. So in machine learning or AI, we often take a statistical inference approach and design data-driven methods. So we have our own tools, such as graphical models, neural network, or deep learning, or variational Bayes to describe complex patterns. But machine learning models, even though being efficient and can be realistic for real-world data, when we use machine learning or AI to model physical systems, sometimes they don't have good interpretation. They're being black box models. More importantly, we cannot guarantee that the predictions from machine learning models are physically meaningful. So the idea behind physics-guided learning is to combine the two worlds together. In this way, we can encode physical constraints or inductive biases into machine learning systems such that we can help machine learning methods to generalize to on-scene scenarios and new situations, and most importantly, to increase our trust in artificial intelligence. In today's talk, I will give you one example of how we can design physics-guided learning to accelerate turbulence simulation. So turbulence modeling is a fundamental task in science, from ocean science to atmospheric science. As an example, here is a video of a three-dimensional turbulence known as Rayleigh-Bénard convection. It happens when the cold fluid in the on the top interact with a warm fluid in bottom, which creates complex turbulence. This resembles the dynamics of a phenomenon known as El Nino, when the warm fluids from the North America interacted with the cold fluid from South Africa. So to simulate this video alone would take several months. Now, goal here is to design surrogate deep learning models that can quickly predict the evolution of turbulence without going through complex numerical integration. So this is a work done by my PhD student, Ray Wang, and our collaborators at Lawrence Berkeley National Lab. It was published at KDD in 2020, one of the leading data science conferences. So for turbulence modeling, it is a classic field that have been studied in science and engineering. So recently there has been a lot of interest in designing surrogate deep learning models to predict the evolution of turbulence. But the limitation for this work is that they often assume that the underlying turbulence has no external force, such as gravity, and they only focus on spatial modeling, where our focus on temporal modeling. In this case, we wanted to forecast the evolution of velocity field of a turbulence. There's also work about physics-informed deep learning, which essentially use auto-differentiation in deep learning to solve a partial differential equation. But in this case, they also require explicit boundary condition inputs, which are not available in the setting of forecasting. So there's also in computer graphics, people study fluid animation for movie production purposes. But in fluid animation, emphasis is more about the simulation realism, which means it only has to look good, but it doesn't have to be physically meaningful. So there's no physical interpretation for the animation of fluids. Our work is also related to video prediction, where given the past frames of video, we want to forecast the future frames of video if we think the velocity field of turbulence as a stream of videos. But for natural video prediction, they often deal with complex noisy data, and there's no physical process that can govern the dynamics of this video. So our key contribution in this work is a hybrid model framework. We know that turbulence is governed by Navier-Stokes equations, which are a set of differential equations that describe the motion of viscous fluids. So we looked into the field of computational fluid dynamics simulation, or CFD. We discovered there are several classic techniques, such as Reynolds averaging, which means we will decompose the velocity field W over space x and time t into two components. A temporal averaged component, W bar, which is computed as the convolution filter G over time, and the residual term W prime. The second set of technique is known as large eddy simulation. It actually computes the spatial averaged velocity field. So it also decomposes the velocity field W over space x and time t into two components, and one of them being the spatial averaging. So this type of techniques essentially exploit the multi-scale behavior of turbulence, shown on the right plot. This plot shows the energy spectrum over the wave number, meaning the size of the scale of the waves. So large waves or large turbulence often have higher energy, where small waves or small turbulence have lower energy. And when we apply Renz or Elliot's techniques, we're separating the turbulence according to their scales. So in the traditional CFD techniques, people often need to design the filter G of S or G of X given C manually. And these type of techniques are not scalable. And sometimes the manually designed filters can be unrealistic. So our key idea is actually leveraging deep learning to learn the filter automatically from data. And we actually combine the Renz-Elliott coupling together, leads to the Renz-Elliott coupling techniques. We can see that we are decomposing the velocity field into three components: the spatial averaging component, temporal averaging component, and the fluctuations. So for both the temporal and spatial averaging filter, G1 and G2, we can replace these filters with trainable neural networks. And that leads to our proposed model, which we call turbulent flow net. So a turbulent flow net is nothing but a multi-layer convolutional neural network architecture. So in this case, given the velocity field W, we will pass it into a spatial filter, which is a multi-layer convolutional network, and that leads to the spatial component. And then we feed the residual into a temporal filter, which is another convolutional neural network that gives us the temporal averaged components. And then we will model the fluctuation separately. So for each of these three components, we will instantiate a UNet, which is a state-of-art segmentation techniques for in computer vision. So it uses an encoder to encode the velocity field into high-dimensional latent representations. And for each of the components, we use separate encoder, E of W, with a shared decoder to model the interactions across scales. So for each of the UNet, it basically is a multi-layer convolutional neural network in this right plot with residual connections to alleviate vanishing gradient problem. So we evaluate this model on a data set coming from Raynaud-Bernard convection in 2 dimensions. This RBC simulation had Prandtl number 0.71 with Reynolds number at the turbulence regime. So our setup is to forecast the evolution of turbulence for 60 time step ahead, given the historical velocity field. And the spatial resolution is 6064, and the total size of the data set is 10,000. So when we look at the forecasting performance of our model compared with a large set of baselines, on the left plot, we're showing the forecasting root mean square error versus the forecasting horizon 60 time step ahead. What we're comparing is a set of deep learning models, including UNet, GANs, or ResNet, and convolutional LSTMs. So these type of models are purely deep learning models without the physics. And we also compared with a set of hybrid models, including the SST model, which leverage Green's function to solve for Navier-Stokes equation, and deep hidden physics model. These models require explicit input of boundary conditions. We can see that TFNet, our model in blue line, is rather robust against error propagation in forecasting. Most importantly, it can significantly speed up the evolution of turbulence simulation. So this shows the average time per frame for the simulation compared with the numerical method, the lattice-Boltzmann method that was used to simulate turbulence. Our methods cut the runtime by half and is much faster than other deep learning models. So this shows the promise of using physics-guided deep learning models to replace numerical methods for simulating complex turbulence. But that's not the focus of this talk. What I want to show is that this type of hybrid method can actually guarantee the physical consistency of the predictions. So on the left plot, we show the mean divergence of the forecast compared with the ground truth in black. So the lower the better. We can see the divergence of model is very close to the ground truth. And on the right plot, we can show the energy spectrum of the prediction compared with the ground truth. And we can see that the energy spectrum or the energy cascade of the predicted velocity field of our model in blue is quite close with the ground truth. In contrast, the pure deep learning model such as ResNet or UNet completely fails in this case. So this highlights the benefit of combining physics-based intuition with deep learning model to guarantee the consistency of predictions. So when we look at the actual prediction of our model, the top row is the ground truth, the TFNet is our model, and 2 of the baselines from state-of-the-art deep learning models, we can see that the ground truth has very chaotic small-scale dynamics, and that can be precisely captured by our model, TFNet. In contrast, pure deep learning models fails to capture the small-scale dynamics and can only generate blurry videos with circular patterns. We also conducted an ablation study of how this model is able to separate the scales into spatial, temporal, and fluctuation components. So TFNet is our model's prediction, right? And then temporal, you can see that the temporal is large scale and the fluctuation becomes much higher frequency, which shows that the model can capture the small scale dynamics and separate scales automatically through this kind of model design. So that's it for our talk, and you can check out the code and the data on my website or follow me on Twitter. And I want to thank the sponsors for supporting our work.
Rose, thank you so much. That's a fascinating talk on how to bring physics into the turbulence modeling and make it faster and better and have physical consistency. That's just really interesting. In the interest of time, I'm again going to suggest that we move directly on to the next speaker, the last but not least, Haonan Chen, who will speak about deep learning for precipitation estimation and nowcasting using operational radar and more multi-source in situ measurements. Topic close to my heart. Take it away, Haonan.
Okay, thanks, John. I'm going to switch the gear from modeling to observation processes using deep learning. So the topic here is about precipitation estimation and nowcasting using radar and multi-source gauge data. I'm Haonan Chen, assistant professor at Colorado State, and I want to acknowledge my collaborators Greg Prater from NOAA GSL and Chandra from CSU, Rob and Elizabeth Thompson from NOAA PSL. Oops. Okay. So compared to point-wise surface hydromet stations or satellite, so radar has a unique advantage in observing weather events in multi-dimensional perspective and in both good spatial and temporal resolutions. So actually, radars are the cornerstone of the National Weather Observation Network. It's used for all sorts of applications in hydrology and meteorology. And now all of the radars are running in the so-called dual polarization mode. In addition to conventional reflectivity and Doppler measurement, we do have a few more variables, including differential reflectivity, ZDR, and differential phase, and the correlation between the different polarization channels. So all of the polarimetric measurement, including reflectivity, ZDR, KDP, etc., sort of representation of the precipitation physics or macrophysics. I would say that's the underlying physics in this type of AI applications. So given the precipitation macrophysical information like the particle size, shape, distribution, or orientation, we can actually infer the precipitation type or precipitation intensity from the radar measurement. So the multi-dimensional and multi-parameter radar measurement are kind of an ideal candidate for AI applications. So in our group, we have been using AI for weather radars for quite a number of years, including radar data quality control and precipitation classification, estimation, and nowcasting. So in the next few slides, I will quickly introduce some of the work about precipitation estimation and nowcasting. And as many of you know, traditionally, radar rainfall estimation start from ZR relations. Now we have dual polarization measurement. So we have a few more power law relations like here. So basically, for given precipitation macrophysics, we build the relation between radar measurement and rain rate. And sometimes, or actually most of the time, the different power law relations here are combined based on certain criteria such as precipitation type or precipitation intensity. So the problem with this type of algorithm is that when we do the nonlinear regression between radar measurement and rainfall rate, so we have a large parameterization error in the regression process. So the question we want to answer here is, can we use machine learning to reduce this type of error? And the other background is we now have tons of data to train machine learning model based on the radar measurement. So on the right, what you see is a NOAA MIDIS system. Basically, it's a data collection and the distribution system. So far, we have more than 40 Starlink gauge stations over the state. So you can tell from the figure here about how dense the MIDIS network is. This is for the northeast part. But in our demonstration work, we'll use the southeast part because we got a lot more heavy rain in that region. So get into a little bit more details in the, I'll move the cursor a little bit. It's popping up all the time. People want to join the session. So for the QPE, we tried a few different models. This is one of them. It's basically based on the ResNet neural network. And this is a simple difference between residual block and the general plane network. So we stacked a few residual blocks here. And for each residual block, we have 2 3x3 convolutional layers. And also periodically, we double the number of filters to extract more information from the multi-dimensional data. And for the interesting of time, I'm going to skip this. So, but the key things here is when we implement the model, we use multi sweeps from the operational radars. And for each sweep, we use multi-dimensional data. So essentially at a single gauge location, we use 3 tilts from the radar, 3 lowest tilt, 0.5 degree, 1 degree, and 1.3 degree. And for each sweep, we use reflectivity, differential reflectivity, and KDP with 3x3 dimension surrounding the rain gauge location. So essentially at a point gauge location, we have 9 3x3 features covering all the polarimetric measurement. And we train the model using 3 years of data from 2016 to 2018. And then we use the data from 2019 for test purpose. This is a quick snapshot of the derived product. So we have 4 panels here. The last one here is essentially based on the deep learning model. And the upper panel, A and B, are based on ZR relations. One is the Neckrat ZR relation. The other is the Marshall-Palmer relation. And this panel here is based on the dual measurement, or based on the operational algorithm implemented by the operational radar. It's essentially based on reflectivity and differential reflectivity. So if you look into the 4 figures here, so overall, we can tell they all give us the same or similar pattern of precipitation because they are all based on real observations. But at the same time, if you really look into the machine learning based result, we can tell the N estimation from traditional power law relations are significantly alleviated, especially over the intense rainfall region and even the region near the radars where the rainfall is not that intense, but still the N estimation was basically corrected. So for quantitative evaluation of the QPE product, so we take into account all the intense precip events during 2019, the summer season. There are about 15 events covering about 40 days. So this is the result. So we have 3 panels here. A is based on ZR relation, and B is based on Z and ZDR, and C is basically from the machine learning model. So we can tell the normalized standard error is increased by 30 or 35% based on the independent gauge-based evaluations. This is really promising. So switching the gear a little bit, for nowcasting, which is essentially a sequence-to-sequence prediction problem, we have tried a whole bunch of algorithms, including our own extrapolation algorithm. So here I'm going to show 2 of them, actually 1 of them, but I will compare with 2 other approach. This is the model structure. It's essentially a UNet model. and we select a 600 kilometer and 600 kilometer area with 1 kilometer resolution. So for this UNet model, we have 4 layers for both encoder and decoder part. And this is the details of the number of filters and how we train on process with the UNet model. And a couple of things I want to mention. And the first one is essentially we use 5 continuous radar images to predict future 30 frames, which is about 3 hours in lead time. And the other point I want to mention is the design of the loss function. So we have actually tested a few of them. And the one I want to highlight here is basically combining the so-called balanced mean squared error and the cross entropy loss. So the combination here is really to highlight the impact of strong radar echoes, just to make sure we predict the intense rainfall really well. So in defining the balanced mean squared error, we essentially add a weight to the mean squared error based on the reflectivity values. So with that, we trained the model using 2 years of data, and we tested with a different year, focusing on intense rainfall events. So this is an interesting result for the Hurricane Harvey event. So on the upper panel, on the left, is basically the 30 minutes prediction, and on the right is 60 minutes prediction. And the figure on the bottom is the corresponding observation or the truth. So we can, if you check the 2 plot from the upper panel and the lower panel, we can tell, although the structure is smoothed out a little bit after using the UNet model, but the intensity and the overall pattern is very well captured through the nowcasting process. So this is the comparison with other approaches. I included 2 here. One is track. I guess some of you guys know that. It's basically a traditional extrapolation method. The other one is called TRAGRU. It's basically based on an improved convolutional LSTM. It's a typical recurrent neural network model. So the takeaway message here is the UNet model, as a very simple model, it can outperform the track extrapolation method and achieve a very similar performance to the a more complicated RNN model, which is really promising. And currently we are working on the generalization capability of both rainfall estimation and rainfall nowcasting model. I can tell you a quick finding is when we implement a trained model in one region to different regions, we want to really quantify how much new data we need from the new region, especially when we have a model or when we have a region where we don't have a massive amount of historical data for training. So this is the ongoing progress. With that, I'll stop.
Thank you very much, Haonan, and what fascinating results on how relatively simple deep learning can use contextual information to improve radar precipitation estimates and nowcasting. Really, really fascinating. So with that, we've come to the end of our session. Please do send Haonan and the other speakers some questions and comments. And many thanks to all of our speakers, Nicole, Amy, Jason, Julien, Rose, and Haonan for excellent thought-provoking presentations. And also to Lindsay from ESIP and Jordan from the Logistics Organizing Committee to helping make this a successful session. Again, let's keep this conversation going on the Slack channel. And now welcome everyone to take a stretch break and then plan to join our next session in 15 minutes. It's a plenary session on trustworthy AI for social good. You won't want to miss it, starting at the top of the hour. So thank you, everyone. Thanks again to our speakers, and see you soon.